Testing, testing. Sound. 1, 2, 3. Oh, oh no, it's gonna oversteep. Oh no. You feel that mass under her neck? Did you feel the mass? Just that whole thing is a huge mass. Yeah. She hurled and it's swollen. It's not bothering her. It's not particularly painful. You could see you could palpate it and she didn't react. So here's what I'm thinking. I think she's Where am I? No, it's in the Chem Biochem folder, and I think it might be in the working copies. It's the usual label, 37, 38, or whatever. Okay.
Oh, man, I hate to be a bearer of bad news, but it looks very itchy. It looks very pixelated.
It's not as bad. It's not as bad as it was yesterday.
Okay.
Mine was usable.
Okay. I guess. Do you think they'll be able to read this live, especially? Oh wait, I guess these were posted, but the review isn't.
Yeah, but these are always hard to read. The groups of 4.
Sure. Yeah.
We're talking, guys. Sorry, we're just babbling around here trying to decide.
Oh wait, actually, it looks fine now.
We're trying to decide how good the live stream looks. We're having so much trouble with it. Stand by for a second. So, welcome, last day of Chem 1. Oh my goodness. The funny thing is, I wish I could say like, oh, I'm gonna miss you guys. That sounds bad. Oh, I wish I could say I'd miss you. I didn't get to meet very many of you. I didn't get to meet anyone in person, and that's such a bummer. It's certainly what makes the class fun for me is to meet you guys. I've been through the material a lot, and that's fun. I mean, this semester we did a lot of new stuff, and I know some of it was distracting to you. I'm so glad you guys have bared with us, and I hope we get some good feedback and some good stuff on the evaluations. Definitely fill out the course evaluations. We'll send you a link again. The course evaluations help us. They help you make Cal better, and we don't get to see them. They have no effect on your grade. We don't even get to see them. They're in the lockbox until after final grades are submitted. So speak freely, speak openly. It's not going to affect your grade in any way. So just tell us what you think. There's a couple questions on it, and those of you who've done it already can see there's some questions about the online part. The university's interested in that. How did this go? How did you experience this? This is really the first semester. This summer was a test of what's going to happen now in the fall. Lots of online. So let's get started. One of the things that you miss, unfortunately, in Chem 1, if you take it here in the summer and you're not in Pimentel, you know we have a little bit of a rivalry with the junior college across the bay. And there's some history to it. And some of you who are new to it might not know that history. But every year we play Stanford, and we call it the big game. And it's a lot of fun. Long-standing rivalry. We battle for the trophy, the axe. And one of the best weeks in your experience. You'll have a lot of fun when you get here for a fall semester where people are here. So hopefully fall 2021, you'll see that. But I'll try to give you a little bit of taste of big game week. What happens in Chem 1 for the big game. So we'll go over to the other computer here. And this is Chem 1 fall 2018. About this time of year when you're talking about titrations and the here's Chem 1 lecture fall 2019. Cal band just bursts into the lecture hall. You might recognize some of that. So this is Professor Phil Geisler doing the fall semester. The Cal band busts in, interrupts the lecture. You could see they were talking about the iodine vapor solid transition. There it is on the bench. So one reason the Cal Stanford rivalry is so strong and vigorous and known across the country is there was probably the greatest play in college football history in the Cal Stanford game in 1982. And I'll set up for you. So Cal and Stanford came down to the last minute. Cal drove down, scored a field goal, went up 19-17. They had Stanford backed up on their own 17-yard line, it was 4th and 17, I think. So it looked like the game was in the bag. Stanford's quarterback, John Elway, you may recognize John Elway's name. He went on to play for the Denver Broncos, all-star quarterback, won a couple Super Bowls. He brings Stanford back from 4th and 17 with, there was 53 seconds left. He brings them back to within field goal range. So with 4 seconds left, they kick a field goal and go up by a point. And we have 4 seconds left in the game. All that can save the Bears is a miracle. So let's look at what happens on that kickoff. This is the call by Joe Starkey, the Cal play-by-play announcer. This is the kickoff.
Harmon will probably try to squib it, and he does. Ball comes loose, and the Bears have to get out of bounds. Rogers along the sideline, another one. They're still in deep trouble at midfield. They tried to do a couple of... The ball is still loose. They'll get it to Rogers. They give it back now to the 30. They're down to the 20. Oh, the band is out on the field. He's going to go into the end zone. He's going to go out of the Bears have won. The Bears have won. Oh, my God. The most amazing, sensational, traumatic, heart-rending, exciting, thrilling finish in the history of college football.
So Cal wins the game on the last second 5 lateral play to cap that off. Now that is called the play. Everyone knows the play. Whenever they have a greatest plays recap of college football, that one is always the last one they show. It's the standout play for Cal victory. Then we do something fun. We have a titration where the solution starts out red and white, an awful shade of cardinal red, I think. And that is titrated. Here we have Professor Maida singing.
We are sons of California, fighting for the golden blue. Sounds and story and titration, so we'll all be through. Stanford's ready to be routed by laboratory, and when we start to go, the red will turn to blue. In this hour of chemistry.
Cardinal and white to blue and gold. The big guy in titration. So a little taste of the fall semester at Cal. Hopefully you'll come and we'll be back in session, maybe even in the spring, hopefully, certainly by next fall, and you'll get a taste of that kind of excitement on campus. So speaking of excitement on campus, it is our last day. We're going to review a little bit today, so nothing that you see here today will formally be on none of the new material. We're going to finish up thermodynamics and kinetics. There are no homework problems on this last kinetics versus thermodynamics. So you'll look at the chem quizzes. So understand the chem quizzes in this section and the ideas of how kinetics and thermodynamics are balanced together. And then on the exam, there'll be some qualitative questions looking at pictures like this and demonstrating your knowledge of kinetics is the reaction rate. Thermodynamics is after the reaction has come to equilibrium. Thermodynamics tells you about equilibrium. Everything before equilibrium is kinetics. So it's the action of the molecules bumping into each other that makes kinetics go. So we did this chem quiz yesterday. So if we have some reactions, this is a simple reaction, A going to B, and we can talk about the rate of that reaction, and we say the rate is proportional to the concentration, and we went through this at the end of yesterday, right? So we'll go through this quickly. Rate proportional to concentration and this thing called the rate constant. The rate constant contains all the information about temperature, about it contains the whole idea of how the molecules are coming together and colliding. Not every collision is successful. If every collision was successful to make a reaction go, then it would be very dependent on just the concentration. But it's dependent on many things. So this K encapsulates the whole idea that there's this activation barrier and there's things that have to happen just right to get the reaction to go. Otherwise, it's proportional to concentration. The more collisions, the more higher concentration, the more collisions you'll have and the better chance of a reaction happening. So kinetics is all about this collisions, this interaction between the molecules. Thermodynamics is all about the energy differences and what happens in equilibrium. So we can talk about a forward and a reverse rate. So the forward rate proportional to the A concentration, the reverse rate proportional to the B concentration with their respective rate constants. And at equilibrium, the forward and reverse rates are the same. That's our understanding of equilibrium. There's not a macroscopic change anymore. The reactions are still going, but forward and reverse have the same rate. And we looked at that with a little animation yesterday. We had pretty slow internet, so it wasn't a beautiful animation, but you guys can play with it online. The forward and reverse rate being equal is our equilibrium condition in terms of kinetics. And then we said our equilibrium in terms of thermodynamics was the ratio of the concentrations, products over reactants. And that is related to the kinetics by the ratio of the forward and reverse rate constants. And that's the overall encapsulation of the relationship between reaction rates and thermodynamics. We can look at it a little bit more because we understand the distribution of energies in a solution. So this is review now of our kinetic molecular theory, a gas phase reaction. This activation energy, that's the energy that the reaction has to get over. The particles have to have that much energy to get to products. It's the barrier, the activation barrier between products and reactants. And that much energy is required. So this could be representing a sample at low temperature. A sample at low temperature, there are not a lot of particles that have the activation energy, an energy above the activation energy. So this is a kinetic energy in this case. So this is the cutoff in kinetic energy, and there are very few particles that have that. Of course, a particle with very high, we know that there are some particles with very high velocity. It's a distribution, and a very high could still collide with a lower energy particle. The total energy of those two make the reaction go. But in general, not a lot of particles have that. So not a lot of successful collisions in the bulk sample. So, that's a little messed up in animation order. So that's a low temperature. If you were to go to a higher temperature, we know from our kinetic molecular theory that curve shifts. The RMS root mean squared speed increases with temperature by the square root of temperature. And this is a curve at higher temperature. All the particles have there's a higher mean kinetic energy for the particles, and there's more particles with a mean kinetic energy greater than the activation energy. So much more likelihood of particles coming together with an energy greater than the activation energy. So these particles here are more likely to have successful collisions. It still depends on, the success. You could bump in the wrong orientation to have a reaction. And we talked a little last time about how a catalyst, often one of the ways it lowers that activation barrier is it encourages the successful collision. That is, it orients the molecules so that when they come together, they're in the right configuration to have a successful reaction. And enzymes, those biological proteins, they really do that. A molecule will fit into a space, a pocket of the enzyme. Another molecule will come in, and they'll be held together, and they can have that chemical reaction. So we lower the activation barrier, we catalyze the reaction by the stereochemistry, making sure the steric factors, the arrangement factors are correct. We saw that happen on hydrogen gas blowing over platinum. The hydrogen gas is absorbed on the platinum surface, so the oxygen gas can react with it efficiently, and that heated up the platinum. And it heated up the platinum. That was the thermodynamics part, that release in energy independent of, as we know, the mechanism. It doesn't matter how the chemicals come together to do a reaction. Doesn't matter the pathway. If you get to products and you get to equilibrium, thermodynamics tells you where that equilibrium lies, regardless of the kinetics. So they are completely distinct, but you can see somewhat related because of that forward and reverse rate and the activation barrier. So that animation somehow messed up. This is demonstrating more particles with the correct activation energy. So you can look at these rate constants as a function of temperature, and you're not responsible for any of this mathematics. Here is the relationship between K and T and the activation energy. So this K is indeed takes into account the activation energy, this constant in front, taking care of the kind of steric factors, the percentage of reaction, the percentage of collisions that will be successful, and the temperature. And it turns out low activation energies and high activation energies, here's two possibilities. And because of this relationship, higher activation energy is more sensitive to temperature. So if you, the rate constant changes more dramatically per degree Kelvin for high activation barriers because of the form of that. So let's just talk through a chem quiz based on that. For the following reaction, the forward rate is much bigger than the reverse rate. So which is true for the equilibrium constant for an increase in temperature? So here it is, the activation energy, K forward, dependent on that. Here's the chemical reaction. So if K forward is bigger than K reverse at equilibrium, then K is bigger than 1. That's a spontaneous reaction. We know that K is the ratio. The equilibrium constant is the ratio of little k, the rate constant, over the reverse reaction. So a fast forward and a slow reverse reaction, the reaction lies towards products, which is a K bigger than 1, a spontaneous chemical reaction. So you can see that rates relating directly to the free energy difference. And why is that? Well, this kind of gives us an idea. So what happens here? So you realize that if this activation barrier is for the forward rate, then the reverse rate has this activation barrier, this energy to get over, a higher hill. And this one is going to be a little more sensitive to temperature. This one will change faster with temperature than this one, because of that form of the equilibrium or the rate constants. So Kf is greater than Kr. So we can see the activation barrier for the reverse reaction much greater than the forward reaction. So the reverse is more sensitive to temperature. So as the temperature goes up, the reverse reaction starts to get a little more, its rate increases faster than the forward reaction. It's not that this activation area energy is getting smaller. Activation barrier is staying the same. It's the temperature factor and the fact that this is a bigger number. This rate just changes faster with temperature. So the reverse rate starts catching up to the forward rate as the temperature increases. So if this is the ratio and this reverse rate is getting bigger, then K, the equilibrium constant, is decreasing. You might look at this and say, well, this is an exothermic reaction. Exothermic reaction, heat is a product. So if you increase the temperature, which way does it go? Back towards reactants. K gets smaller. The same conclusion from both the kinetic and the thermodynamic argument. And when we said heat is a product and did that Le Chatelier's principle, that was a hand wavy kind of, okay, let's think about heat as a product. This explains that in terms of the kinetics. And that change, we know that thermodynamics can't care about the rates and the change. That's why adding heat as a product is kind of a hand wavy way to mix kinetics and thermodynamics. here's a formal way to come to that same conclusion that separates the thermodynamics and kinetics, so that you can see it's a change in a rate, not a change in any of the thermodynamics. The enthalpy change is still the same. It's this rate changes, not this distance. That stays the same. That's thermodynamics. But the rates change disproportionately. The reverse rate changes faster than the forward rate because of that large, the rate of change of the rate depends on the magnitude of the activation energy. So let's just summarize that then. Here is the reaction coordinate again, the generic progress of the reaction. Here's an exothermic chemical reaction. You're certainly meant to recognize that by this time in your career. This is an exothermic. Heat is released. Reactants higher in energy than products. Activation energy high for that reverse reaction. That's an exothermic reaction. The reverse is more temperature sensitive than the forward reaction. If you have an endothermic reaction, we recognize that as endothermic. You have to have energy put into the system because you end up at a higher energy than you started. And now you have an endothermic reaction where the forward rate is the one that's the more temperature sensitive because of that high forward activation energy. So we can rationalize the things we understood about the size of the equilibrium constant in terms of reaction rates. These dotted lines indicate a catalyst has been added. A catalyst lowers the activation energy but does not change the energetics, does not change the thermodynamic, does not change the equilibrium position, it does not change the energy released. If you take nothing else home from Chem 1, take home the fact that adding a catalyst does not change the energy released. It changes the rate that we get there only. So catalysts are valuable. You know that if we had hydrogen and oxygen, and we wanted to get that energy out of hydrogen and oxygen coming together to make water. If we had them in a balloon, we'd have to sit there and wait forever for them to react because that rate is extremely slow. The kinetic barrier is too high. But you put platinum in there, and platinum catalyzes that reaction, and we can get that heat. The reaction goes fast, and we can get it in a controlled way. That platinum heats up in a controlled way. We get the energy out, and we can use it because that platinum is heating up. So catalysts extremely valuable. The reactions in your body catalyzed by enzymes, your body could not function because the reactions that happen in your body have high activation barriers. The enzymes catalyze those reactions. So those reactions can go quickly in your body and the energy localized so it can be used by your body. So that's just summarized here, the things you need to know about the interaction between kinetics and thermodynamics and the catalyst. So those are all the take-home lessons. This is the kind of the extent of what you'll need to know for the final exam. So we're trying to take it easy here this last 2 days and just give you qualitative things to work on and understand, give you a chance to breathe as you're studying for the final. And here I've reminded you that in a catalyst that does not change the thermodynamics of the system. Okay, lovely. So which of these has the lowest activation barrier? We've seen blowing up water by adding a flame, blowing up hydrogen and oxygen, having that explosion. We've seen the reaction in the presence of platinum, and we've seen hydrogen and oxygen sit in a balloon. So which of these has the highest activation barrier or the lowest activation energy? And we won't even vote on this one. I think we've said it a million times. If you take nothing else home from Chem 1, take home the fact that a platinum, a catalyst, reduces the activation energy. These two, you add more energy to get over the barrier. So you have to add some energy. Here you don't have to add anything. The activation energy comes down. And this just represents the same activation barrier for these two. That's a good exam question. Which of the following have the same activation energy? Mark all that apply. This one and this one have the same activation barrier. You're just adding energy for this one to get over the activation barrier. Here you're changing the activation energy with a catalyst. Oh, goodness. So the answer here, the catalyst lowers the activation barrier. Which has the largest K? Mark all that apply. Oh, can't say largest and mark all that apply, can you? Mark the reactions that have K equal, it would be interesting on the exam. You could say, which of these has delta H equal, this is the explosion reaction, minus 400 and yeah, it's a bunch. It might even be more than, I can't remember, is it thousands of kilojoules per mole? We don't know, this is just an example, but say delta H is some number, some exothermic number. Which of these have that delta H? Mark all that apply. Now it doesn't matter the mechanism. We've talked about this many times. It doesn't matter how you get from hydrogen and oxygen to water. The thermodynamics is path independent. You would have to mark all of these. Those all have the same equilibrium constant and they all release the same amount of energy. Okay, we should have done that one as a chem quiz. But we have a bunch of chem quizzes coming. We're going to do them. Remember how we do our reviews. We'll have some chem quizzes that you can do together and think about that summarize things. That was a beautiful summary of everything you know about thermodynamics and kinetics was encapsulated there. So all of these have, none of them have the largest because they're all the same, I guess. All of them are the same is the point there. So there we go. We're going to talk now a little bit because I know so many of you are MCB. We're going to do a little bit of review in terms of biological molecules. So we'll continue this process we're doing of reviewing the whole semester within the context of biological molecules. Now, again, remember, you're not responsible for any structures or any biological processes, none of that. We're looking at them as examples of the concepts that you've learned and you have in your arsenal. And you see already in your arsenal, just from Chem 1, you can understand biological processes. All of biology is just chemistry. In fact, all of everything in the universe is just chemistry. If you want to go into MCB, that's great. If you want to get your PhD in molecular biology after you leave here, it's okay to be a chemistry major. In fact, it's better to be a chemistry major. Learn the chemistry, learn the details now. It's really easy to pick up the biology in graduate school. Biology is not complicated. It's the chemistry that if you know intimately, you'll be a better molecular biologist. That's just my, I don't get paid by the department. Well, that's a lie. I do get paid by the department, but I don't get paid by the department to plug the program per se, but I'm plugging the program. Be a chemist first if you want to go into any kind of biological molecular science. I mean, it has the word right in it, molecular biology. So let's look at a few of these examples. Here, ATP, adenosine triphosphate. This is the famous energy storing molecule in biological chemistry. In your body, energy is stored in ATP. So you metabolize the compounds that come into your body, the sugars and the fats and the proteins. You metabolize them, you burn them, there's thermodynamics happening, but the energy can't be used right there usually. So it's stored in these molecules called ATP. And you'll often read, I've said this before, that it's stored in something they call a high energy phosphate bond. I hate that. It's not a high energy bond at all. It's a low energy bond. And we know that now. We'll talk about it again in review here. This is just a structure. It's an adenine, a ribose. So it's a nucleic base, and it's a sugar and 3 phosphates. And you know now, if those are phosphates, then there's a phosphoric acid possibility. There's protons, acidic protons at all those positions. And we've talked about that a lot. So here are the 4 acidic protons. Those have a pK around 6. This one here on the end, a pKa of around 2. So what is the charge state of this molecule at pH 7 in your body? We could do that as a chem quiz. What is the charge state? You have this proton, this proton, this proton, and that proton. They have different pKa's. All of these about the same. If you're at pH 7, that's basic compared to, it's on the basic side, higher than 6 and much higher than 2. So at pH 7, all of these are in their basic form. Basic form is the proton is removed. When the proton is removed, all of those have negative charges. What's the ratio? Well, these were about pKa 6. You're at pH 7. So if you do the math, that's a 10-to-1 ratio at pH 7, 10 times as much base form as acid form. So it's not all base form. It's still in equilibrium. And at pH 7, there's 10 times as much base form as acid form. This one here that had pKa 2, that's a factor of 5 pH units, 100,000 times more base form than acid form. It's a very charged molecule, highly charged, 4- charges at pH 7. That's one reason the separation of that bond releases energy, because of all the charge separation you get when you hydrolyze that bond. So it's a combination of things that make that a good energy storage bond, not a high energy bond. So here I put it in quotes. I've been using air quotes. High energy phosphate bond, that's garbage. It's not a high energy bond. It's a low energy bond. That's why this reaction works. You form more high energy bonds, and the release, the separation of all those negative charges, is a release in free energy. There's a lot of hydration that goes on. It's very complicated, of course. The actual reasons for the release of that, some of the reasons are simple. You break that bond, but you make stronger bonds. But there's also that charge dynamics that releases some free energy as well. So when you hydrolyze this in water, you adenosine diphosphate. You remove one of these phosphates, and you get phosphoric acid there and the H+. So that reaction is exothermic, releases free energy, and this state is lower in free energy than that state. And there's your phosphoric acid in the singly protonated form at pH 7. It's about a mixture. The pKa of phosphoric acid, it's the first pKa is 2, the second is 7, and the third is 10. So phosphate HPO4 with its pKa, its middle pKa of 7, is an excellent buffer for pH 7. Weak acid buffers around their pKa's. So an excellent buffer for pH 7. So that reaction releases free energy. There's the entropy and the enthalpy change. So here's a good chem quiz. Oh, I think it is a chem quiz. Let's just do it. ATP hydrolysis, I was going to ask you over what temperature range is that spontaneous, but I think that's an actual chem quiz, so let's get to it. Here's the reaction kind of in pictures, the bonds that you form and the bonds that you break to make that reaction go. And we're saying that the bonds you form are stronger than the bonds you break. So bonds broken minus bonds formed, overall exothermic. So here it is. Here's that question I was going to ask you. So let's think about this briefly. So in the 1990s, life was discovered thriving around thermal vents in the ocean. Deep ocean, they're near volcanic outlets. The water is very hot, well over 100 degrees C. You'd think it would be sterile, no life. Because everything should, that's how we sterilize things at 1 atmosphere of pressure. We boil them. But at many hundreds of atmospheres of pressure at the bottom of the ocean, it's well above 100 degrees C, but bacteria live there. They're called thermophilic bacteria. So can they use ATP? Can they use that hydrolysis reaction as an energy storage and an energy source? Can you hydrolyze ATP at well above 100 C and still release energy? Release free energy. Free energy is what you really are interested in. We didn't talk about that a lot in this class, but the free energy is the usable energy from a chemical reaction. The enthalpy tells you about the energetics, the bond energies, and the Coulombic interactions. But some of that you can't use. Some of it gets lost in entropy. Some of it gets lost in disorder. Disorder is hard to use. We know that when you want to do work on something, you have to have a concerted motion. So you have to have organization. But entropy is the ultimate disorganization. So you lose some of your useful energy as entropy, but the free energy is still a measure of how much energy is useful. So think about this for a minute. Melissa, are you ready to start a chem quiz? Oh. Melissa will start the poll. Take your time. You guys can start thinking about this and voting. And you've got something going for us, Melissa? So I will go to Melissa's screen. Now, we had some trouble doing this. Okay. We think we're going to get Melissa's screen. We don't know if you'll be able to switch back and forth, but we're going to look at her screen here for a second. There it is. Perfect. Okay, I'm going to go back to mine then. Oops. I'm going to go back to my screen so I can give you guys that group of 4. What you need to answer that isn't actually here. I'm sorry. We had delta H was something like, well, let me just tell you, it's negative. Delta S was positive for this reaction, the hydrolysis reaction. I hope I'm giving it away by telling you the sign of those two things. Okay, we'll cruise right along here. I'm going to talk through these. I want you to think about them a little bit, but I know it's the last day. We want to get through our review. So we'll go to Melissa's display and look at the results of the Chem quiz poll. Yes is overwhelmingly true. They do live, and I think you would guess yes, even if you didn't understand exactly the thermodynamics, because they are alive, and you wouldn't expect them to have evolved a completely different biology, and they haven't. But you could say that it's okay that they have that, can use that ATP to store energy because of these two things. You can plot the free energy difference as a function of temperature. You can see, is that going to release free energy over a broad range of temperatures, over 100 degrees C? And when you plot it, delta G standard is delta H standard minus T delta S. Plot delta H or delta G versus T, you find I have a negative enthalpy. So the intercept is negative. Delta S is positive. So positive times the negative. T is always positive. So this is Kelvin. We're not plotting in Celsius. We never do that. So T is always negative. So minus T delta S is always negative if delta S is positive. So we have this negative slope. So free energy is positive for all, or excuse me, negative. This reaction is spontaneous at all temperatures. So that's a great exam question. Over what temperature range is that hydrolysis spontaneous? You can figure that out from the thermodynamic parameters of the reaction. So let's look at the catabolic reduction of sugar. This is glucose. So this happens in your body. Glucose reacts with oxygen to form carbon dioxide and water. We've said that many times. You breathe out carbon dioxide and water. This reaction happens differently in your body than it does when you burn glucose over a flame in the lab. But we know thermodynamics says the path doesn't matter. If in the lab you can get out your 300, I think this is a 3,000 kilojoules per mole reaction. If you can get that out in the lab, your body can get that net amount of energy out. Path doesn't matter for thermodynamics. So let's look at this. Here's the sugar molecule. This long line here just indicates that this is a ring. So this guy is connected to that guy. So you have to break all these carbon bonds, and you have to make carbon dioxide. I'm interested in the oxidation state. So what's the oxidation state of that carbon? Well, if you go through the our Lewis dot structures and how we assign these oxidation numbers, we can assign the oxidation numbers of the products and reactants here. The products are the carbon dioxide and water. And we know we've done this a lot now. The oxidation number of that carbon is 0. The oxidation number on the carbon when you get to carbon dioxide plus 4. So that's a formal oxidation. The oxidation number increased. We have carbon is oxidized and oxygen. Here's molecular oxygen. Obviously, oxidation state 0. There's no preference for electrons either way if they're homonuclear. And the oxidation state of oxygen over here, -2. So the oxygen is reduced. The carbon dioxide is oxidized. When you talk about oxidation number, it's not confusing. If the oxidation number gets smaller, if it's reduced, then that's a reduction. We're not trying to be mysterious there. If it's not a reduction, it's an oxidation. So that's how I remember it. So the oxygen is reduced. So how does that happen in the cell? This is amazing how this happens in the cell. You would not believe it. And the decades of work of molecular biologists who are good chemists. This is related to the work that I did in my graduate career. I was a structural biologist. I used nuclear magnetic resonance to determine the structure of biological molecules. So the structure of those proteins, how do they fold up and what do they look like at equilibrium was how what I studied for my thesis work here at Cal. So here's the mitochondria. You may recognize that term mitochondria. Again, none of this biology is on the exam. This is all just examples of all the chemistry we've learned in a biological setting. So the mitochondria are little organelles within the cells of your body. They're known as the powerhouse of the cell. It's where ATP is made so that it can be used in the body. So ATP is made from ADP and free phosphate. You make that bond that you're going to break later. So you can make that bond, take the ATP somewhere else in the cell and use it somewhere else to do chemical reactions. So this is the mitochondria. There's an intermediate space. The mitochondria has lots of membranes. Membranes are this blue and yellow we have here. They are hydrophobic and hydrophilic molecules that naturally form a bilayer and that separates spaces in the cell. In this case, both of these spaces are inside the mitochondria, separated by a membrane. There's something we call the intermediate space and the matrix, the deep interior of the mitochondria is the matrix. It's actually funny. I don't know if this was intentional. It probably absolutely was not. But you guys probably know The Matrix, the movie. And in The Matrix, the movie, the machines take over and they're ruling the world, and they use human bodies as batteries. They have them in these large farms and they use them as batteries, and they create this artificial reality for the humans that are batteries, and that's called the Matrix. It's interesting that that's called the Matrix, and mitochondria really act as batteries, formally act as batteries. They move electrons around electron transport chains and form electrical and proton potentials that are the energy source for phosphorylating ADP. So I'm absolutely sure that that doesn't have any connection. It's just a coincidence, but it's a hilarious one. So carbon, here's the sugar going to the carbon dioxide. This is done anaerobically within the mitochondria. Oxygen is not involved in this step. So this is done anaerobically. It's done by the actual formal oxidation of the carbon to carbon dioxide, the breaking of this molecule with enzymes to form this carbon dioxide. When you do that, you are obviously releasing all the hydrogen atoms of that sugar, and they're released as protons, and those electrons that came off the carbon, it went from 0 to plus, so electrons coming off the carbon, this is the battery part, are transferred through the membrane by special proteins embedded in the membrane and little carrier molecules that carry the electron and proton to the membrane. And then the electrons are transported. There's an electron transport chain in the membrane, and protons pumped out from the matrix to the intermediate space. So there's some chemistry we understand, oxidation, removing electrons, and it's happening in this isolated way. Now, oxygen dissolved in the intermediate space is brought through and combined with those electrons. So the oxygen is reduced remotely from the actual oxidation of the carbon. And that more of these protons from this reaction are over here. They can react with that oxygen and these electrons to form water inside the cell. That also reduces the H plus concentration. So H pluses are pumped out here and then they're used up. So you're pumping them outside and you're using them up inside. So you're getting a net excess of protons in the intermediate space. You're using the free energy change of oxidizing carbon dioxide and reducing water to form that gradient in pH, gradient in proton concentration. Then there's a remarkable step that happens where you have an excess of protons here in the intermediate space. How come I've lost animation? Somewhere there was a little dot on the board. So now you have a pH gradient, and then these excess protons are channeled back through. And you know, here's thermodynamics again. You have excess protons here, deficit here. The universe hates that. The universe wants to equalize the pH. So there's a free energy difference between the inside and the outside membrane. And as you let those protons back in, that catalyzes the reaction of ADP with a free phosphate to ATP. Absolutely unbelievable. Yes, there's a question?
On the previous slide, for the oxidation number of the carbon in the glucose, I think it's 0, but isn't it +1?
Carbon, 1 oxygen, 4 bonds, oxygen. So yeah, it is +1. There is 4 bonds, one of them to a carbon. Those are shared. Hydrogen is about equal. Yeah, so the question was, if you have a carbon, it's a question of relative electronegativities. So you had this carbon that I was talking about bound to an oxygen, a hydrogen, another carbon, and another carbon. And you're trying to say, what's the oxidation number there? You draw the Lewis dot structure, and then you're assigning oxidation numbers. So you assign to the more electronegative element all those electrons. And then you're sharing more or less equally these, because those have the same electronegativity. They're carbons. And then the hydrogen has, and carbon, you have to compare those electronegativities. And do I assign the electrons to hydrogen or carbon? If they're absolutely equal electronegativities, then you would say that the carbon has a +1 because it has, it has 4. You compare how many electrons are around it in this molecule. So you would say, well, these I have to share because they're equal. These two, I'm going to decide whether I share them or not. These two I assign to the oxygen. That's more electronegative. So the carbon has 1, 2, 3 here in the molecule. In the atom, it has 4. So it has an oxidation number of +1. It has 1 fewer electrons. So it depends on, do I assign those two to the hydrogen or the carbon, or do I share them? And the calculation there is the carbon is slightly more electronegative, so the carbon gets both of those. That would give you a 0. If you assign them, shared them equally, you would get a 1. So on the exam, I'm not going to get into electronegativities that are that close. So this one is obvious. The fact that those two are equal are obvious. The relative electronegativity difference between carbon and hydrogen is very close. In the calculation that I had to give a 0 there, the carbon, I assigned both the electrons to the carbon. Good catch, very nice. I certainly would have accepted 0 or 1 for that, and we wouldn't have gone there. We wouldn't have gone to elements that are so close in electronegativity. In general, I would call them equal. Either way, it's an oxidation. This remarkable reaction occurs, and you just have to stand back in amazement. And this is about as disjoint a pathway as you could imagine to get from sugar to carbon dioxide in water. Yet, thermodynamics tells us we get that same amount of energy out, regardless of how we do it. That's coupled to, that is forcing a pH gradient that is coupled to phosphorylating, adding a phosphate to ADP to make ATP. This transmembrane proton here, this ATP synthase, it's huge proton, huge protein, many, many subunits. And this thing, you wouldn't believe it, it actually turns like a motor. It's as if the pH, the protons coming through are hitting a paddle wheel. And that thing moves in the cell as the ATP are made. And that motion couples to bringing a phosphate and an ADP together and squishing them together into an ATP. Unbelievable sophistication in this, in your body. You go, evolution, holy mackerel. How the heck did that happen? So beautiful biochemistry there, and just fascinating. So here's a animation, an electromicrograph of a mitochondria that's been enhanced and colored and made beautiful. The question is, how does the pH in the mitochondrial matrix compare to the intermediate space? So there is a pH gradient. So which has the higher pH? Go ahead, we'll start a chem quiz. We'll just give you a 30 seconds on this. Where is the higher pH, the intermediate space or the matrix in the mitochondria as ATP is being formed? Did we start a chem quiz?
Yes.
Okay, let's see. 74 responses. Go ahead and just tell me. We won't even switch sources here. Oh, we're quite spread out.
Most people said A.
Most people said A. So I'm saying that there's an excess of protons here relative to here. So if there's more protons here, this space is more acidic than this space. More acidic is a lower pH out here than in here. So that was the idea here. You're lowering the you're raising the pH as you force those protons out. This is higher, more acidic out here, higher concentration of H3O+, higher concentration of protons is a lower pH. So excess in the intermediate space means a lower pH. I'll let's sit that up there for a second. So super cool. So let's look at the global process then. The 1 mole of glucose being catabolized to form carbon dioxide and water in that amazingly elegant battery pH gradient in the mitochondria. 3,000 kilojoules. We actually saw that back when we burned the donut in oxygen. That's about 3,000 kilojoules per mole. That is used to phosphorylate ATP to ADP to ATP. So I go down in free energy here. I go up in free energy there. And then elsewhere in the cell, I take that ATP. I get 38 moles of ATP formed for every mole of glucose that I catabolize. I use that. One of the ways I use that is to take free amino acids and make proteins. So this is building. This is how your body builds and grows. Of course, many other things happen in the cell, but the main function of the cell is to make proteins and maintain nucleic acids. So that is the general overall pathway. You get about 4 moles peptide bonds from your 38 moles of ATP. So a mole of glucose, you end up making about 4 moles of peptide bonds. So how many protons is that? Well, 4 moles of bonds is a lot of bonds, as you know. So you can make lots of peptide bonds. You can make long proteins of 4 moles of bonds. So billions and billions of bonds to make your long proteins in the cell. How efficient is it? The breaking down glucose in the cell, the combustion of glucose in the cell releases 3,000 kilojoules per mole. About how efficient is it? Stored as ATP. So how efficiently is that 3,000 kilojoules per mole stored as ATP? Energy is lost all over the place. As you know, you would guess it's certainly not 100% efficient. If you were just going to guess, I would always choose the lowest possible efficiency in these situations. A biological process can be extremely efficient because of using the enzymes and getting everything really close together. If you're looking at the free energy released when you burn your octane, when you burn your gasoline in your car, you could calculate the efficiency of that. The maximum efficiency you could get is if you used every kilojoule of free energy to make, to convert every joule of free energy to work. That's the maximum you could get. You obviously, as you know, get much less than that. You do friction and in the engine, all the moving parts, gases escaping, all the imperfect things. We'll just talk through this. So again, it would have been nice if you had numbers here. Good thing we're talking through it. You do want to do some numbers to figure out your 38 moles of ATP, how much energy you released. So you would have to multiply 38 moles of ATP by the free energy released per mole of ATP. So we'll just go through that calculation and give you the numbers. 3,000 kilojoules per mole of glucose is released. This is a good question for the exam. How much energy is released when 30 moles of ATP are hydrolyzed? Well, we saw the free energy release was 30 kilojoules per mole. So about 1,200 kilojoules to make your 38 moles of ATP. So you had to burn 3,000 joules worth of glucose. You only were able to capture in your ATP 1,200 of those kilojoules. The other were used up elsewhere. A lot of it as heat. You know, your body heats up, your body, and essentially that's not wasted. That keeps our body warm. So we'll take it. So that's how much you capture. That's how much you use. It's 40% efficient. But as we said, we'll take that waste product. Heat is a waste product. We'll take it because it keeps us warm. Excellent. How many grams of glucose then are required to make a mole of serum albumin? That's a very common protein in your blood. It's about 100 amino acids long. So you have to make, for a mole, you have to make 100 moles of amino acid. You have to make 100 moles of peptide bonds about for a mole of serum albumin. Avery's scratching in the corner and banging on the door. So a gram of glucose. So now you have to convert grams to moles of glucose to get the energy released by a gram. Multiply the mole of peptide bonds times the energy of a peptide bond. You don't even have to do that because you know the efficiency now. So let's use the efficiency. I think I use the efficiency to do this. We'll talk through this. There are the peptide bonds in this protein. So individual amino acids here. You can see their various side chains. Here's a side chain here. Here's a side chain here with your threonine and your tyrosine. You don't have to know that. That is there's a glycine here and oh geez, I forget. Dave Whammer would be so upset with me now that I can't tell you what that amino acid on the end is. He was my PhD advisor. I was actually a nucleic acid chemist. I did the structure of nucleic acids, DNA and RNA, not proteins. But let's just talk through this in terms of efficiency. So you want to make 100 moles, 4 moles of peptide bonds per mole of glucose, 100 moles of peptide bonds. You could get that from 25 moles of glucose. So you use the efficiency there and say that's the 40% efficiency. Then you say a mole of glucose is 200 grams. So you need 25 moles times 200 grams. You need 5,000 grams. You need 5 kilograms of glucose to make 4 moles of peptide bonds. So 5 kilograms of glucose, you know that's around 12, 15 pounds of sugar. You can imagine down in the 15 pounds of sugar, 12 pounds of sugar to get your peptide bonds. But remember, this is moles of peptide bonds. So this is many, many moles of peptide bonds. It's many, many moles of protein because proteins, we saw that one had 100 peptide bonds. So 100 of those bonds per protein, 100 moles of those bonds per mole of protein. So, but that tells you why you have to eat and drink every day. Okay, so there's a review of a lot of the chemistry we've learned. We can now do some formal chem quizzes to review a lot of the other chemistry we've done in the last 8 weeks. It's an exhausting amount of chemistry. I'm amazed that anyone gets through Chem 1 in 6 weeks. You really have to focus and work hard, much harder than doing it in the fall. And doing it remotely without everyone around you and the support is even compounds that. So here, let's do this. That's the answer. I got these in the wrong order. So 23 grams of sodium is added to a 20-liter vessel at room temperature and a pressure of chlorine gas of 2 atmospheres. So what's the pressure of chlorine gas? Partial pressure of chlorine gas. Maybe it's the only gas, so it's total pressure in the flask. Wouldn't matter if there were other gases in the flask. You could still calculate a partial pressure. You could calculate the pressure from just the chlorine. You could add it to the other pressures from the other gases to get the total pressure. The sum of the partial pressures is the total pressure. Each gas independent. Each gas thinks it has the entire volume to itself. So to calculate a partial pressure, you use the entire volume and the overall temperature and the number of moles to get a partial pressure for each gas. And you can add those partial pressures up. Here you have to do a chemical reaction. 23 grams of sodium. Turns out, don't have a periodic table at our fingertips here. Molar mass of sodium is 22. So you have about a mole of sodium there. You have about a 20-liter flask at 298 and 2 atmospheres of chlorine gas. So you can use the ideal gas law now. So I can use here I can use my definition of a mole. So I have 23 grams of sodium times the fact that there's 1 mole of sodium is about 23 grams. So I have about 1 mole of sodium in there. That's from the very first day of class, second day maybe. Our amounts of stuff, we go to the gas law, the ideal gas law, to say I have about 20-liter flask at room temperature with 2 atmospheres. Here, I wouldn't use the ideal gas law per se. I would just remember at 298 K, 1 mole of gas occupies about 20 liters. 22.4 liters is the standard molar volume of an ideal gas. So if I have 2 atmospheres at that, under those conditions, 1 atmosphere would be 1 mole at 22 liters and 298 K. So 2 atmospheres must be 2 moles. You could also just go through PV equals nRT, the ideal gas law, to get to your 2 moles. So now I use my stoichiometry. I can just probably go back to the slide here. 23 grams is about a mole of sodium. 2 atmospheres of chlorine gas at 298 K and about 20 liters is about 2 moles of chlorine gas. And then you use the stoichiometry, sodium plus 2 chlorine. Sodium ion plus a chlorine ion makes NaCl. We know that happens. That's the ionic reaction. Let's just write sodium solid plus Cl2 gas goes to NaCl, the white solid. In order to balance that, I need a 1/2 there. So I use 1/2 mole of my 2 moles. That leaves me a 1.5 moles left. 1.5 moles left under those conditions is 1.5 atmospheres. Start with 2, take away 1/2, 1.5 atmospheres left. Okay, We went on to structure. What is a structure similar to PCl3? So we have 3 possible molecules and ions down here. What has a similar structure? So we write our Lewis dot structures. We use our steric rules, the VSEPR rules, to decide what this shape is. So we can do that. Here's PCl3. I can write the Lewis dot structure for PCl3. I can see that it has a steric number of 4, a bond of a lone pair, and 3 atoms, 3 bond pairs. Steric number of 4 gives me a tetrahedral arrangement of the bond and lone pairs. But that tetrahedral arrangement, we don't call that the shape of the molecule because we don't include lone pairs when we name the shape. So we have a tetrahedral arrangement of the lone pairs and bond pairs. The shape, though, is just a trigonal pyramid because we're going to ignore that lone pair. We call that a trigonal pyramid. The bond angle, something less than 109. 109 is the tetrahedral bond angle. And that is a number that we do expect you to know. The tetrahedral bond angle is 109.5. I don't care that you know exactly what the bond angles are when you have a lone pair here that pushes the other atoms here closer together. I do expect you to know that it's less than 109 because this lone pair squeezes the other bond pairs closer together. It's held quite closely because there's not an atom up there to pull it away. So what are the other ones? Here's sulfur trichloride with a +1 charge. So we do the Lewis dot structure with 1 electron short because we have a plus charge. I haven't shown all the electrons around the chlorine. There's the lone pairs around the chlorines here. Just shown the bond when.
Like a minute ago, I thought it was just me. But... Oh, it came back.
Is it back in more or less real time? How far are we off? It looks like, yeah. Okay, it looks like we had a glitch in the video. You've missed about a minute of me or so. Welcome back. So we were just drawing Lewis dot structures for the 3 molecules here. Sulfur trichloride, count up all the electrons, remove 1. You get a steric number of 4, 3 bonded pairs and a lone pair. Here we have a steric number of 3. I've added in as red dots here all the electrons. Take all the valence electrons from magnesium, all the valence electrons from chlorine, add 1 more for that negative charge, get a steric number of 3. Iodine trichloride, steric number of 5, because you end up with 2 lone pairs on the iodine and 3 bond pairs. Are we buffering and we're stopping again? We're not too far behind. How's the audio? Can you hear me talking? But the audio is reasonably constant. So we got some, Melissa's video is buffering. I don't know how much is buffering here. Our live stream looks good on this end. This is the internet age. A year ago, we could do this with no problem because the traffic on the internet was a fraction of what it is today. Today, we have to deal with everybody trying to do this. So interesting, 3 trichlorides, but 3 different steric numbers. And only one of them has steric number 4 to match the phosphorus trichloride. Which of these ions, now we're into our periodic trends, which of these ions has the greatest absolute value, the the biggest negative numerical value for the electron affinity. Remember, electron affinity is the energy released when I add an electron to an atom. That's generally a spontaneous reaction. Even though an atom is neutral, there is some positive charge that a free electron would see. We know that because we know those outer electrons, there's a significant effective nuclear charge, even for the outermost electrons. So some of that positive charge of the nucleus shines through. And that electron free electron can be attracted to that positive charge and added with a release in energy. As you bring together a positive and a negative charge, the energy drops. We've seen that. So which of them releases the most energy, the greatest negative value? 3 ions here. The ions are going to have a high electron affinity because they are positively charged. They're fully positively charged. These could be atoms, and you would still have a negative electron affinity, now much bigger. So the electron affinity is, or the, here's a reaction I can write. This is the ionization energy written in reverse. When I ionize, I take a neutral species, I go to the positive species and a free electron. That's the ionization energy. The electron affinity is adding an electron to a free species. And in this case, we said the free species was a positively charged ion. So this is the electron affinity written in reverse. So the electron affinity is adding electron. The ionization energy is removing an electron. I've written that one in reverse and that one in reverse, but I know the trend in ionization energies. Ionization energies increase across the periodic table, and then down to potassium, they decrease going down the periodic table. So I can draw this graph, and this you should be able to more or less construct. There are no numbers here, but the trend, chlorine and argon going across the periodic table, and then potassium going down to the next row of the periodic table, next row of the periodic table, you can draw that trend. And those are ionization energies. So the electron affinity written in reverse, the ionization energy written in reverse. Here, we know this one, the ionization energy, that's going in this direction, taking an electron off. So these, did I say that wrong the first time through? Might have said that reverse in the first time through. I hope I'll say it correctly now. This is the ionization energy, taking an electron off and making the positive ion. And that is correctly written forward, that the atom here removing an electron to form the positively charged species and the free electron. That is the ionization energy. The electron affinity is adding, so the electron affinity is adding electron, so that's the electron affinity written in reverse. However, we know those two reactions are identical, one forward, one reverse. So this one, we know going that way, it's exothermic. Geez, oh, Pete. We know going this way, it's endothermic. It takes energy to remove an electron from a neutral species. I have to pull that electron off. Pulling it off is adding energy. So going in this direction, it's endothermic. Going in that direction, it's exothermic. Going in this direction is the opposite of that. So we can see these two things have the same magnitude of energy and with the opposite sign, because that's the activate the electron affinity going in the opposite direction. So if I know this trend for the ionization energies, I know this trend for the electron affinities, and I can put argon with the highest ionization energy as the highest electron affinity, greatest magnitude of electron affinity, adding that electron back to the positive ion. Okay, we know our trends. So we talked about quantum mechanics then and the structure, electronic structure of atoms. Electronic structure of atoms, we looked at orbitals, and we decided that there are many orbitals around every atom. They have different quantum mechanical properties. They have different quantum numbers that lends different shapes and different orientations. We found that each electron has a unique set of quantum numbers, 4 quantum numbers. Every electron can only have, no set of quantum numbers is repeated in an atom. Each electron has its own set. And we said that the energy was actually quite simple, that the energy, we just saw it a minute ago, the ionization energy, the energy for a state is minus z squared over n squared. N is the principal quantum number. Z is the charge on the electron. So this would be, if you had one electron, would be the ionization energy, because this is how much energy the electron has. So we drew these energies where 0 in energy was up here. Our energies were all negative, and the lowest energy, n equal 1 state, was down here. N equal 1, Z is the charge on the nucleus. So hydrogen in 1s1, that electron there has 1 squared over 1 squared negative. There's a factor of, there's a constant in there, Rydberg, so this would be 1 Rydberg of negative energy. That's the energy I have to put in to ionize that species. So I ionize that species, then I look at the photoelectric effect, or just the straight ionization from some source. Here's the kinetic energy of ejected electrons. Here's the energy I'm putting in with photons. So here's the energy of the photons. Each photon has an energy, so energy is increasing here. When I get to photon energies that are greater than that Rydberg of energy, then the electrons are ejected, and any additional energy above the Rydberg that's contained in my photon goes into kinetic energy of the ejected electrons. So the question is, which of these has about that same plot? So essentially, which of these has about the same ionization energy? Which of these has its ground state about here, a Rydberg? So you can look at them all. I probably have that in animated form here. The ionization energy of hydrogen is about the same as helium in the 2 quantum level. So Z2, N2, probably have that written down. Here, Z equals 1 and N equals 1 for hydrogen, 1 proton plus 1. N equal 1 is the quantum number, 1 electron. Helium plus and 1 electron in the 2 principal quantum level. So here Z is 2, the charge on the nucleus, not that charge. That's plus 1 because there's 2 pluses here and an electron left. So Z is the charge on the nucleus. There are no other electrons. So that electron sees that full plus 2 charge, and it's in principal quantum level 2. So Z squared over N squared and Z squared over N squared here are about the same. well, those are exactly the same. As you know, there could be a minor difference in, but not a difference that we really care about. So helium plus ion in the 2 principal quantum level has the same ionization energy as hydrogen in the 1 principal quantum level, the ground state principal quantum level. This is an excited state. It's in n equal 2. It's in an energy level higher than the ground state. So here is the other possibility. Now I have helium with both electrons. So now there's going to be some shielding factor. We know 1s electrons don't shield each other very well. So each of these electrons sees almost a full positive 2 in the nucleus, but not a full positive 2 in the nucleus. And now I am in that lowest energy state, the ground state. So here, Z effective is something slightly less than 2, bigger than 1, but less than 2. And n is equal to 1. So now I have an ionization energy that's greater because I'm close to 2 plus charges in the n equal 1 state. So this electron sees a higher positive charge. So that line is going to be out here somewhere. And here I have hydrogen in the 1s again, and now helium in the 1s 2p. So now I have something very similar to this because I have an electron out here in the 2p. So it's in principal quantum level 2. The p doesn't matter. It's in principal quantum level 2. As far as we're concerned, those all have the same energy, z squared over n squared. It's a 1 electron system. There's an s electron that shields one of the positive charges, but not all the positive charges. So again, this electron sees about 1. S electrons are efficient shielders, but won't shield the whole positive charge. But this electron out here sees 2 here, shielded by 1 electron here. S electrons are reasonably good shielders. So this number is close to 1, probably slightly bigger than 1. So I have 1 for Z effective and 2. So again, that energy, Z squared over N squared, is going to be slightly less than this energy here. I'm going from the 2 shell with about the same charge. So that guy is going to be here somewhere. Okay, that's a lot of chemistry, VZ effective charges, and our photoelectric effect plots, our quantum mechanical structure, electron configurations, all wrapped up there. Okay, we can make molecules. So we did molecular orbitals. Here's fluorine. And again, I will always give you this distribution of orbitals. You don't have to know the ordering, but you have to understand the number of orbitals, sigma and pi star and sigma star bonding and anti-bonding orbitals. So molecules have energy levels just like atoms because they combine their atomic orbitals to form the molecular orbitals, but they're still quantized. There's still quantum phenomena happening there. These are quantized molecular orbitals. We fill those molecular orbitals with the atomic electrons. So we add the atomic electrons from both atoms to form molecular orbitals. The molecular orbitals are filled with all the electrons from the 2 atoms. So 6 2p orbitals, the 3 from each fluorine, form 6 molecular orbitals. And then all the electrons in those 2p orbitals for each fluorine enter into those molecular orbitals. So which is the most paramagnetic in the ground state? You have to add the 5p electrons from each fluorine, so 10 electrons total for the neutral species. So I add them following the Aufbau and Pauli and Hund's rule. Lowest filled first, then pair, then parallel electrons fill. If I have to put more electrons in, I pair them before I go to the next energy level. And I continue to do that until I get to the 10 total electrons. This is diamagnetic, no unpaired electrons. Paramagnetic means I have an unpaired electron. I do the same thing, except 2 fewer electrons from fluorine here, because it has a +2 charge. 2 fewer electrons, I remove the highest energy electrons, and the ground state of this ion has 2 spins parallel in pi antibonding orbitals. It is paramagnetic. F-2, I add 2 electrons to this, and they go into antibonding orbitals as well. That is also going to be diamagnetic, no unpaired electrons. What's the strength and length of the bonds? What's the bond order? So you take bonding electrons, subtract away antibonding electrons, divide by 2. So we have 2, 4, 6. Bonding minus 4 is 2 electrons, divide by 2, 1 is your bond order. Here, a bigger bond order because you're losing anti-bonding electrons, a stronger bond here. 1, 2, 3, 4, 5, 6 minus 2 is 4. Divide by 2 to get 2 electrons per bond. That has bond order 2. And this, you have an equal number of bonding and anti-bonding electrons. That's bond order 0. So this, if you add electrons to fluorine, is likely to break apart. Bond order 0, nothing holding it together. This is the most stable, strongest bond, and this is intermediate to those 2. Woohoo, we went into gases. Here is a PV isotherm on a pressure, temperature, space plot. So the phase diagram, solid, liquid, and gas. The lines represent equilibrium between the solid and the liquid, the solid and the gas and the liquid. These are every point on that line, the gas and the liquid are in equilibrium. These are all different vapor pressures for different temperatures. Which of those lines? They are all isotherms because they're at constant temperature. One of them is at the critical temperature. Above the critical temperature, I have one phase, no phase changes above the critical temperature. Isothermal there, I can change the temperature as much as I want. I can change the pressure as much as I want along that isotherm, and I will never see a phase change. I'll condense it to very dense. I can get it as dense as a solid. I can let it reduce the pressure and let it expand to the density of a gas, but I don't see a distinct equilibrium of 2 phases anywhere above the critical temperature. Here I have an isotherm below the critical temperature. So here, as the pressure increases, I go from gaseous to liquid water, increasing the pressure. Right here, I have an equilibrium between liquid and gas. So which isotherm is water at 270 or 373 Kelvin. I don't think that's much of a surprise. 373 Kelvin. I'm 100 degrees Celsius is 0 degrees Celsius is around 290, 25 degrees Celsius is around 298. I'm above that, below the critical temperature. This represents a increase in pressure at that crosses a phase boundary and has a phase transition. Need some more information there. So we talked about the distribution of speeds in gases, talked about this quite a bit. We came back to it many times. We came back to it for thermodynamics and kinetics. We talked about how energies can be plotted out because these are speeds, these are velocities, and in a gas, the energy is all kinetic energy. It's all related to the speed, and the energy goes as the temperature only. The energy of gas is an ideal gas, 3/2 nRT per mole. We also looked at the average energy per particle, and that's 3/2 K, the Boltzmann constant, times T. So here I am per particle, and I have the Boltzmann constant. The Boltzmann constant is just R divided by a mole. It's just the gas constant per particle. So that's the energy per particle on average. That's the energy of a mole of gas if N is 1. We can find those energies. We could plot those energies because the energy is also, it's all kinetic. So the energy of the gas also has to be mv squared. That's the expression for kinetic energy. You take the mean kinetic energy by taking the mean of the squared speeds. So those energies, because you can find this on the plot, you can find energies on the plot. In this case, we're just interested in the gas, the mixture of gases. We have the mixture of gases at the same temperature. So the gases at the same temperature have the same energy. The energy of the system is the sum of the two energies of the individual gases. The mean kinetic energy of the gases, individual gases, is the same. The kinetic energy depends only on the temperature, not the nature of the gas. But the speeds of the gas are different because the masses are different. So you can have the same amount of energy, but a different distribution of speeds depending on your mass. And here are two different distributions of speeds. One distribution of speed has a higher mean speed. This distribution of speed has a lower mean speed. So you say to yourself, well, if I have to have the same energy, I have a more massive particle, then my distribution of speeds should be smaller. My mean speed, my root mean square speed should be smaller for more massive particles, but gives me the same energy because the product of the two is still the energy. The less massive particle can have a higher root mean square speed, a greater distribution of energies. So I have two distributions. There's a factor of 2 in the RMS velocities, so we can do that math. And we know the RMS velocity goes as inverse square of the mass, inverse square root of the mass. And here doubling the root mean squared velocity, which is what I see here. In order to get a doubling, I can double the temperature or reduce the mass by a factor of 2. Doing both of those would give me the same, would give me twice the VRMS. This 2 comes up into the numerator as a 4 and would give me twice the RMS velocity. So I need a factor of 4 here in the mass, which I get. And here I have a twice the RMS velocity, 4 times the mass. I have the square root. These two have different ratios of masses. So this is deuterium, mass 2 for each of those, mass 1 for each of those. That's mass 4, that's mass 2. And I have the ratio of, I have that ratio, the factor of, did I do that wrong? That has mass 4, that has mass 2. That's a factor. What the heck did I ask? What are X and Y? And it's the same temperature. And I doubled the VRMS. So I double the VRMS. So to double the VRMS, I have to go. What did I do? I need a factor of, to do double the VRMS, I need a factor of 4 in mass. Yeah. No, I agree. Yeah. Yeah, yeah. Why didn't I put the 4 right there? That's what I'm saying. that would have done it. If I have a 4 in the denominator, that would put a 4 up here. Take the square root of that, and I get twice the RMS. Mass divided by 4. Bring that 4 up into the numerator.
But the temperature is double. Why is that 800 K?
Oh, I'm sorry. There are 2 different temperatures. Sorry, guy. I thought, I was thinking these 2 are at the same temperature, so you had to have a factor of 4 here. They are at different temperatures. So you doubled the temperature and have the mass, then you get the same, you get that doubling in VRMS. Lord have mercy. I should look at the darn chem quiz before I walk in here. So to clear that up, sorry. These are 2 different temperatures. It's the X at 400 K and Y at 800 K. So not only is the mass changing, the temperature is changing. So then I can say, okay, if I have both a factor of 2 in the temperature and a factor of what factor in the mass do I need? I know the factor of 2 in temperature. And I get a factor of 2 here in the mass. That gives me that for T over M. So it's 2 times bigger than this one. And that's the factor of 2 in mass. So I need that factor of 2 in mass because I have that factor of 2 in temperature. Goodness gracious. Don't make things worse on the last day. You squirm when you see the Diels-Alder reaction. Why would you even include that? Melissa says. Are anybody left watching? Okay, we'll go for a few more minutes here. We have 70 people watching. So here's a reaction that made Melissa cringe because it's a reaction you're going to learn in your second semester of chemistry, organic chemistry. It's the formation of a ring. Very important chemical reaction because it's hard to form rings. So Diels-Alder, you form a 2 single bonds from this double bond. And the question is, forming those 2 single bonds from the double bond, what is the plot of free energy versus temperature, or natural log of the equilibrium constant versus 1 over the temperature for this reaction? So you need to know the relative enthalpy and the relative entropy change. I think delta S is obvious. You go from 2 moles of molecules to 1 mole of molecules. So that's a decrease in entropy. Enthalpy, you have a net change here of, you have 1 single bond there. You have 1, 2, 3 double bonds. So you break 3 double bonds, you make 1 double bond. So you have to, the net is 2 double bonds broken. You break 1 single bond and you form 1, 2, 3, 4, 5 single bonds. So you net make 4 double bonds or single bonds. So you put in enough energy to break all those. You release enough energy to make all those. But you can say, well, there's a make and a make, break and a make there. There's a break and a make there. So those cancel out. Effectively, you break 2 double bonds, 2 moles of double bonds, and you form 1, 2, 3, 4 moles of single bonds. And you know these energies. So you break 2 moles of these guys, you make 4 moles of those guys, and this is more than half of that. So net, when you're making those bonds, is exothermic. So delta H is bigger than 0. So we can use the relative bond energies. If you didn't understand my doing it quickly there, in my head, you can add and subtract all the bonds broken minus the bonds formed. I just said net break of 2, net make of 4, and I realized there's 4 of those is more energy than 2 of those, so you release more energy than you put in. That's an exothermic reaction. So exothermic reaction, don't remember how much animation I have here. Net decrease in molecules, that gives me delta S less than 0. A net of 2 carbon-carbon double bonds broken, but you get 4 carbon-carbon single bonds. So that means it's exothermic. So delta G, delta H minus T delta S. So delta H is negative, it's exothermic. So I have to have a negative intercept. That one has a negative intercept. That one has a negative intercept. Delta S is negative. Times a negative means a positive slope. There's only one positive slope. So this one is delta G minus T delta S. Delta H minus T delta S is that one. If I want to plot natural log of the equilibrium constant, I can plot minus delta H over T plus delta S over R. The slope is determined by delta H now. Here the slope is determined by delta S. It's determined by the opposite sign of delta H. The intercept determined by the sign of delta S. The sign of delta S is negative, so it's one of these two. The slope is the opposite of the enthalpy sign. Enthalpy is negative. Opposite of that is positive. So positive slope, look at that. Delta H, delta G, and ln K versus T for this reaction have the same plot. Neato. Okay, that covers a lot of the stuff we have done before we got to acids and bases. Acids and bases are relatively fresh in your mind. So we covered a little bit in our biochemistry. So what was I supposed to tell them? Course evals, to finish your course evaluations. And then you asked me something about the relative proportions. Was I supposed to say that out loud? On the exam, the last stuff, the acid base stuff, will be weighted slightly more than the rest of the semester, but there's a lot of the rest of the semester. So you might see something like 1/4 or probably less of the questions, more or less about the last 2 weeks. But I mean, what does that matter? You have to study everything anyway. So any other questions? Again, here's how we're going to write the exam. We're going to look at all the chem quizzes for the whole semester, and we're going to come up with questions based on those. Look a lot like those for the qualitative conceptual questions. We're going to take questions from the homeworks over the whole semester, and we're going to look at those for the quantitative questions. So you should recognize a lot of what you see, and then we're going to have a couple, as many as not many. What do we say, about 4 just creative questions that we come up that blend as much of the things together as we can. Okay. There's a question, will there be a lot of math for acid-base questions or more conceptual? It's going to be something like equal-ish, we hope. Like I said, just for the whole exam, we're looking at the chem quizzes you saw and the homework that you did. So you'll be doing some of that icebox stuff. That pH is pKa plus log of the relative concentrations for your acid-base stuff. But you'll also be qualitatively looking at the shape of titration curves, and you'll be saying if pH is close to pKa, that means they're equal concentrations, bigger concentrations, that kind of qualitative comparisons of things. The relative size of the K gives you the relative strength of the acids, that kind of qualitative stuff is there. That qualitative determination of acid strength, the polarity of the bonds. A strongly polar bond is a weak acid. We talked about having an atom with a high oxidation state kind of removed in the molecule somewhere, 1 or 2 bonds removed from the proton, and that high oxidation state made a stronger acid, weakened that bond. So that's qualitative stuff. Yeah, so that kind of stuff.
Will we have to understand titrations of weak acids with weak bases?
Do I have to understand weak acids with weak bases? Well, yeah, you have to understand everything we did. So go back. So I flubbed. We talked in circles about our weak acid with weak base titration. It was a mess when I did it in the lecture, but we fixed that in the recording. So Ryan and I stayed after, we stayed after class, and we re-recorded that section. And then we spliced it in to that lecture. So there's a better recording, and that will show up in Prism when you see a question that has weak acid, weak base in it. You'll have that section of the video, or scroll through the video till you see that chem quiz and replay that.
It's kind of menial now, but I think we forgot the R under the entropy. Or wait.
Yeah, the gas constant here. It doesn't matter for the shape of the line, of course. So if we were calculating this number, we'd need R here. If you have problems during the exam, you can email us during the exam. We don't want you to have a lot of windows open in your browser, but if you're not seeing the images or something, there's something that's preventing you from continuing, then email the GSIs immediately so we can see if we can fix it, or we can make some of accommodation for that. I think we can restart you in the middle by pressing a button, so you can refresh everything, save your previous answers, and let you continue. So yes, email us in real time if you're having trouble with the exam. And we're talking technical difficulties. Of course, you can't email your TA for advice or any help with the actual chemistry. Do I have a lifeline? Can I use one of my lifelines? There are. Sorry, no lifelines. Anything else?
No cheating.
And no cheating, please. You know, we can see where you switch in your browser, and you know we were devious last time. We weren't devious. We just had you calculate. We told you what to do. Calculate the enthalpy from the numbers you had. Don't go look it up. If you looked it up, you got the wrong answer. One reason you got the wrong answer, when you looked up that enthalpy of formation of ethanol, I put the enthalpy of formation of the gas, I think, is what I wanted in the exam. And if you just Google it, you get the standard state. So that's the enthalpy formation of the liquid. So neener. Any other questions? Okay, well, I wish I had met you guys. Please look me up. Come by and say I had summer Chem 1. If we ever get back to campus, you can find me in the campus directory. I don't know where my office is going to be, actually. I think we're changing offices, shuffling around in my building. But you'll be able to find me somehow. Good luck. TAs wish you well. I wish you well. We'll get the final grades up as soon as we can after you're done. And you'll be able to see them online in B courses. Bye. You want to come up? Come up and say bye. Melissa is here. We all say bye and we love you. Good luck.
Goodbye.
All right.